Welcome to week 4 of firmware training. We will be covering, so last week we covered registers and timers, PWM, some binary and hexadecimal bitwise operations and masking. And we'll be carrying over, I think, a couple of the topics we covered here. This week, though, for the presentation, we'll be going over just kind of common communication protocols. So that includes kind of SPI, I2C, UART, USB. You may have heard of someone. You've probably heard of USB, but some of these other ones, they may be new. So we'll be covering those. And then we'll just talk about bits on sensors and I2C implementation in ATmega 32AP, which will lead directly into the lab for this week. So I guess we'll start with communication protocols. So there's kind of like two large ways where you can kind of overall describe most electrical communication protocols. You know, we're not talking about English, right, as our communication. We're talking about digital signals for the most part. I say for the most part because there's you can sometimes use analog signals, but we'll get into that. But overall, there's usually kind of two large fundamental groups, which are kind of serial communication protocols and parallel communication protocols. So a lot of the ones we'll be talking about today are going to be serial based, but parallel is pretty common on your motherboards for your PC, and are often kind of move a lot more data. So serial is you kind of just have one stream of information coming in from one source into one input with a clock, and then they're stacked in a row, and they're just kind of sent from the same one pin to the other pin, while parallel is as you would say, parallel, running multiple streams at the same time with that similar clock functionality. But like I said, I think actually all the protocols we'll be talking about today are going to be serial protocols. I mentioned clocks. What are clocks other than the things that tell time? Fun fact, they actually do a similar thing on electrical systems or firmware systems. So they're usually a kind of a square wave of a known frequency. It's often called like the baud rate. You may also see it as that. They use the edge of this square wave of a constant frequency to sync data reading across devices. So as we kind of get into the protocols, you'll see that we'll start like reading, an input, or we'll start writing an output based on when that clock is either rising. For this example, you see it's on the first edge. I know it's repeating function, so I guess first edge is relative, but this first rising edge, at that point, the device would be looking at this input, and they would be seeing it's a 1, and the output actually, covers that, right? It's a high bit, and then you'll go low, of course, because in order to go high, you have to go low. But then you'll come back up again, and you'll kind of do the read at that cycle. And as you can see, in the middle of this low clock cycle, we don't really care about, but that's actually when the transition occurs. But then we'll go high again on the clock, and it appears as the low signal. So that's kind of what the use of a clock is, and it applies outside of protocols. It runs with our, we talked about it last week with our timers. There is a clock that the timers operate at, or a certain frequency in which the values in the timer accumulate, all based on that clock still. But for us, we're going to be talking about it as kind of like the read cycles, or I guess the write cycles, effectively communicating between two devices on two or more than two communication devices on a protocol. So there are synchronous communication protocols which would use this clock that I just described, and then there's asynchronous, which do not use a clock, and they usually embed that information within the packet itself. So the first communication protocol we'll get into is SPI. So it is full duplex. So what that means is that Data can go both ways at any time. And then we have three devices, or the devices share three lines to kind of enable this. So there's always one, or line being, a wire or a PCP trace, whatever. They share three connections. So the one is MOSI. So we have the term master and slave. The master can kind of control the bus, and then the slave responds with information based on the requests of the master. So we have MOSI, which is master in, slave, or sorry, master out, slave in, acronym, and then MISO, which is master in, slave out. So those are repeated here. And then you have the clock, which we were just talking about on the previous slide, that is set by the master as well. And then the last element is a chip select. So the thing with SPI is you can actually have multiple devices on the same bus. But what you do is you activate the chip select. So say you had, 4 different devices that are connected to the one main controller. You can use the chip select to only talk to one at a time. So you can actually share these 3 lines between, I think it's 255 actually, but we'll say n number of devices, and select which one you want to focus on using the chip select. But the master controls the clock, and like I said, the chip select chooses between each of the devices. Of course, when you have multiple devices on the same bus, that will reduce your effective communication time between master and slave, because, one at a time, because multiple will be trying to do the same operations on the same bus. But if you only have one SPI port, then having multiple slaves on that with appropriate number of chip selects is kind of convenient way to do it, we'll say. So then the next protocol is I2C, or TWI. You probably will rarely see it called TWI, but I2C is technically a copyrighted term for this protocol, and TWI is just another company's version. But the gist is that it's synchronous, half duplex, one way at a time. So we were talking about synchronous, right? So we still have that serial clock, but then half duplex this time means that information can only go one direction at a time, and it uses kind of capacitance, which this gets a little bit into the electrical aspects, but it uses capacitance for determining which way things will go. So, compared to SPI, where you can have information going both ways at the same time, you can only have information going one way at a time. You can also have multiple devices on, a shared SDA or SCL, but it actually, you would have address, right? So instead of using a chip select, you would use an address. So this would be address number. A lot of times you actually have to pay for a specific I2C address. So we'll say, for the sake of this example, this would have address 1, address 2, address 3, and data is sent using frames, which are kind of ways to encapsulate data. And in that frame, or like a packet, right? That's kind of more often heard the term. This frame will have the address so that each device would know what's being asked of it specifically. But any device can kind of claim being the air quote master by controlling the serial clock. So, but oftentimes, for example, like in the RoboJackets application, we'll just have a microcontroller that talks to some type of sensor or device that will be kind of, the microcontroller is constantly the master. But sometimes, if there's read and write, so sometimes you want to switch it based on the operation. So the next protocol is, technically it's RS-232, but it's kind of now often be called UART. UART's actually technically the hardware So like this chip is actually like a UART device, but it's now kind of, commonly called UART communication. So it's asynchronous. It's full duplex. So if we're going back to our terms, asynchronous, there's no clock. Full duplex, data can go both ways. And it only uses 2 wires. And that was another advantage of I2C too. But it uses 2 wires, but you do need to set the same baud rate. So baud, we said, is our clock speed, but you have to kind of set that on both sides independently because there isn't a clock. You can't. Modern devices actually can kind of guess what the clock is, but older devices, they don't know what the clock is, so they won't know how fast to read information or how fast to write information. You might get overloaded, or it might just return garbage data. So if you've played around with the Arduino, if you change that baud rate setting on their serial print, which you can actually do in the labs on the Tinkercad, you might get garbage data. I guess Tinkercad may not simulate the garbage data as much as plugging in a real Arduino, but it's important to set the baud rate to be what you expect on both devices because you don't have that clock. So then we have USB. So when I said it's kind of digital, sometimes it's digital, but it doesn't look like just a square wave. A lot of the other examples that I just talked about, information is encoded with either a high or a low value. However, USB is a little bit different. It actually uses differential pair. So what that means is, if you kind of look at the graph, the D plus and D minus are actually kind of inverted of each other. And you can kind of encode the information by taking the difference between these two. So this allows for kind of more robust, signal integrity, differentially routed. For another example, like Ethernet is also differentially routed, which that can go, hundreds of feet. But an SPI bus, or even more probably an I2C bus, it won't be able to go that far in terms of length of wire or length on your PCB. But the differential pair aspect of USB kind of makes it a lot more noise resilient, and you can still keep your data, because the only thing worse about not getting data is getting wrong data. Or I guess depends who you ask, but still getting no data and getting bad data when you have 2 devices communicating are both really bad cases. So it defines the rate in a clock sync phase. So again, there isn't necessarily a clock signal provided as there were for SPI and I2C. The clock is kind of encoded within the USB packet. So USB, you've probably heard of a lot. You have your tons of devices, your mouse or keyboard or whatever it is. So we often don't necessarily use USB devices between like embedded systems, but we often do it between our microcontroller and our PC. So kind of going over a quick summary, SPI, which we talked about first, kind of you can compare which protocol you think would be most appropriate for your engineering application. So SPI, that was the first we covered. You need 4 wires minimum. You need a clock. It's relatively fast though. And because you have 2 separate lines for communication both ways, you won't get bogged down with, if you have 2 people talking, if 2 people can talk at the same time, in theory, the information can be conveyed a lot faster than one person talks and the other person talks, right? So same exact deal with communication protocols. And in theory, yeah, you can have a lot of devices on your SPI bus. However, as I kind of mentioned before, the chip select line that you need per secondary device, that can add up really quickly. So on a microcontroller, there's a finite number of digital pins that you can use as your chip select. So in theory, it's, you could say, kind of infinite, but in actual practical use, we'll say a lot for now. So next we have I squared C. You need 2 wires minimum. It does have a clock. It's one of those 2. And then it's relatively slow. But the nice thing is you can just chain devices up in a row, and that allows you to kind of reduce the actual number of wires that you need. And you can also address specific devices in the chain as well, which is unique for chainable applications. You have to have a lot more overhead for this, and you would want something chainable so that you don't have to bring long wires all the way back all the time. So second to last is UART. You need 2 wires minimum. There isn't necessarily a clock signal, but you do have to set the same rate, same baud rate, the term, on both, so that each device knows how fast it should be sending and receiving information. Again, speed relatively slow, but it you only need two wires, and I guess we're kind of seeing that a lot of times when you're sharing the same bus for data lines, it's hard to make it go fast. But which would this is why parallels super nice in PCs, but obviously it's a lot more complicated. So there's technically only 2 devices that you can have at a time on UART, because you just set one as the transceiver and one as the receiver, and vice versa, and that's it. However, you can add more hardware using things like multiplexers, that you can switch between a bunch of different devices at once on the same UART bus. And then our last one is USB. So we do need 2 wires. There isn't a clock, but because USB has become so ubiquitous for our computing devices, with the advancement of USB-C, it's actually relatively fast. USB many years ago was probably on the same data rates as UART, but because every device that interacts with a computer is now USB, they've been focused on, they being the USB consortium, has been focused on making the hardware requirements get more specific and more effective, but they can push the speeds of the communication bus. And also with USB, you can technically only have 2 devices, but of course we know that USB hubs exist, which take that same idea of muxing or some other different ways to approach it. That's not even just hardware muxing. It's more like a router or a switch. But so yeah, those are kind of the protocols that we often use on our robots. Of course, there's more out there, but those are the kind of the common ones across all the teams. So some of the teams use CAN, some use Ethernet as well, or wireless protocols. So there's a ton out there, but these are kind of some of the big 4 that overlap. So communicating between devices is good, but it's good to have information to be communicated. So that's kind of where sensors come in. So I guess what is a sensor? So it converts a real world quantity into an electrical signal for our case. So it's kind of used to measure state variables of a robot or system, and it can be digital or analog. And the analog signal, if you've probably seen the analog read on some of these previous labs, that's an analog signal. It outputs the device, if it's generating analog signal, it outputs voltage correlated to a reading. So what it means by that, it's not just a 1 or a 0. It's a variable kind of range between 0 and 1. So if you kind of look at this graph, there's this sinusoidal looking signal, but then you have this blue kind of stair-steppy looking signal, and what that is it's actually being converted from an analog signal into a value that is readable by the computer, which is technically, digital with ones and zeros. But as you can see, this is more than just an on or off. There's a ton more information being conveyed here. And then, so that's kind of all focused on analog. And then digital signal is just, 1 or 0. And, for if you were using the same signal, it would probably just be, 1 up here. And then it would be probably like 0, and then -1. Bad example because it's negative, but it's really just a 1 or a 0 that's kind of conveying it. So, and these types of signals are kind of incorporated into a bunch of different sensors based on like how the values are actually being read. If it's using a resistor, a lot of times there's fancy sensors, but it's really just a resistor divider at the end. That's probably where you get an analog signal. So you can also have, if it's like a switch or something like that, or physical, on-off switch, that would be like a digital signal. So like I said, there's tons of different sensors. There are IMUs, which actually we'll be simulating in the lab today, but they measure acceleration, the kind of rotational acceleration, linear acceleration, rotational acceleration, and just direction with the compass, pointing towards north, right, or magnetic north. So that's one of the sensors. It's pretty common. I think almost all of our robots actually have an IMU on them at this point. So we also have time of flight sensors or distance sensors. How often they work, they either use sound or light and measure how long it takes for it to go from the source to a destination and come back. So those are almost, not all of our robots. They're on RoboNav and they're on RoboRacing and RoboWrestling. But they're good for estimating the distance of between you and the object you're pointing at. We have encoders and potentiometers. They're super good for measuring an angle, or rotational amount, or how often the thing is spinning. And we also have a current sensor, so that measures the current flowing. So that's often seen on our motors. So we see that on RoboCup, and we see that on RoboWrestling too. Along with IGV or RoboNav and RoboRacing, I think actually all of them have current sensors at this point. Some other sensors, you probably heard of a camera, right? It's technically a sensor. Takes in light information with different filters and presents it as lots of ones and zeros, measuring the magnitude. Kind of a crazy way to think about it, but at the end, cameras are a sensor, and use them on a lot of our robots, RoboRacing, RoboNav, RoboCup. We have LiDAR, so that's actually very similar to the time of flight sensor. However, it's usually rotational, so it's usually covered in 360. But LiDAR, similar deal. They shoot a laser and see how long it takes to bounce back, and you can kind of do that many times a second, and spinning in one axis, and you can actually map out how far away objects are from you on that one plane. There's also even 3D LiDARs, which of course do it in multiple dimensions. So you have these crazy maps of objects away from, or points away from your robot. So we see that in a lot of now self-driving cars are using LiDARs. It's the spinny part on the top. And then we have GPS, which we've probably all been exposed to. GPS, but there's satellites around the globe, and you kind of triangulate between them, and it gives you your approximate location. So when you have sensors, you need to sample them. So we have this thing called a sample rate. So sampling is just like looking at a instance of a value. and the sample rate is how fast you can do that. How many times a second can you read a sensor or a real life signal, right? So if you have something spinning at, we'll say 1 time a second, there's actually this this theorem made by Nyquist, which we have honored him on the right, that says that you need the sample rate to be twice as fast as the frequency of the thing that you're measuring. And if you don't do that, then you're not fully capturing the full signal. It would be kind of like if you're on the, like on a sine wave and you keep looking at, the one location where it's low, right? You'll think, oh, the sensor's always low, right? But it actually goes high and low. But if your sampling rate is not high enough, then it may appear that it's always low, right? That's kind of a rough example of that. But anyway, it's the Nyquist theorem, or your Nyquist rate is often, it's best to be at least 2 times the thing you're trying to sample. But it's always perfectly fine, usually, to be more than that. Depends on the processing capability of the thing that's sampling. Another thing with sensors, bit depth, and there's quantization. So if we go back a ton, this is actually an example of quantization. You're turning your analog, variable signal into discrete steps. And the amount of steps that you take between, the lowest point and the highest point would be the bit depth, is the actual number of steps. But, you have to take that in consideration. If, for example, if your battery voltage is at, we'll say 20 volts, and it's supposed to be at 24 volts, but you can't see the steps, or we'll say it's at 22 volts and it's bad if it's at 20 volts. If you don't have enough steps on your reading, you may not be able to, sense that it's at the minimum it could be. So bit depth is important for being able to capture a sufficient amount of information that is useful. It's keeping the number of significant digits to an extent that you need. So here's kind of like a visualization of quantization and bit depth. So it's, you can kind of cover how many parts of the steps can you cover with 2 bits. So it'd be, 0 and 1, 1, 0. There's only so many different combinations of 2 bits you can have to kind of evaluate a signal. But as you kind of, increase the number of bits, this also actually takes into account as you go down the sampling period as well. But as you can kind of see, the signal, this was originally a sine wave, gets closer and closer to actually looking like a sine wave at the end when you boost the sampling period and increase your bit depth. You can really fully capture the signal, but that costs more. It often takes longer to capture this amount of information, and it's usually more expensive on your sensors. So it's really often a trade-off between price, size, and things like, quantization error, which would be how much off your value is from the real value based on the size of these steps. Oh, look, I got right into error already. So error is, of course, when you try to, look at information with the sensor, there's going to be reasons why it's not 100% correct. The amount of error may mean that you can't use this specific sensor, right? If you're trying to read a value and you can't tell the difference if it's just static noise or it's like talking to somebody on the cell phone. If it's too staticky, you're not actually talking on the phone. It's just, you're just hearing a bunch of noise. So same thing here with sensors. error terms are kind of added to the true measurement of the state variable, so it kind of shifts it away from what it actually should be. So we often hear the term noise. There's actually kind of a specific terminology for error between noise and bias. Noise is zero mean with high variance, so it averages out to be zero, but the values get pushed high and low. And then a bias is a non-zero mean, low variance. So what that would be is just like it's constantly always shift up, right? So if you can look at the this diagram over here to kind of show it, low variance, low bias, yeah, it's closest to the center, which is what you want, of course. But if you have the high variance, which would be, I guess, high amounts of noise effectively, the values are, if you take the average of them, they are pretty darn close to the center, but they're all kind of scattered around. And then if we look at the bias, it's just kind of just shifted away from the center. Our readings are consistent, but they're consistently shifted, so you may have to account for that. And then if there's high bias and high variance, then you're running into some fun filtering issues that you'll have to deal with on how to try to get it back close to that center. So sources of error in like sensors or in your system: temperature, EMI, vibration, and even quantization error I mentioned. So kind of ways to reduce error. You can kind of take a calibration, and this is good for accounting for bias, right? So if you're at your initial calibration, you're always at 5, but you should be at 0. You could just subtract, it's 5, 5, 5, 6, 5, right? You could just subtract 5 all the time. It's probably close enough, right? And then and you can add 2, right? It goes both ways. And then noise, you can take multiple averages or multiple samples, right? And we say zero mean, right? We can take multiple samples, so we'll take all of these different values. You add them up and take the average. Then it's actually close to the center. So you can kind of use estimation or filtering algorithms to get rid of that noise. It's often high frequency noise, which is a problem. All right, so that's all about sensors and communication protocols. If y'all have any questions, just ask them in the chat, and we'll try to answer them. Or we can just of course, ask them at the end. So yeah. Now we'll talk about kind of a specific example of a protocol. So we'll be talking about implementing I2C/TEWI. So as I kind of said before, I2C have frames or a packet. There are kind of like it's consistent sets of ones and zeros, and information being conveyed so that two devices can successfully communicate and pass information. So there's a start condition. So that is a way for the receiving end to say, okay, I know this is the start of the message. Then you have your address frame. We were talking about how you can chain I2C devices together. So you use that address frame to say, okay, I only want to specifically talk to device number 3. And with that, I'll use address 3. Usually, like I said before, you don't have controls oftentimes of what the address actually is. But in theory, it has a unique address, and you can kind of talk to a specific device. Then you have a read-write bit. So that's pretty clear. Usually, it's either read is 1 or writes 1, and it's the opposite of it's 0 for the other. But that's how you can kind of tell the difference between if you're requesting information or looking for information. Then you have some other acknowledge bits, and then you have your actual data that's being encoded. So this is usually a register and a value if you're writing, or they're reading. It's usually just the register. and then you have your stop, right? So then you know when the beginning and the end is. That's the full message, and then the receiving end can process the middle parts because they know where they are. There can consistently be address in the beginning. There's consistently going to be the data in the middle and the end. So the ATmega 32AP, which is the chip that's on Arduino Unos, and it's the the board we've been using in all those Tinkercads that we've done before. We'll go into how kind of its I2C module works. So there is a buffer of values. So a buffer is just an accumulation of values, way to store it. To be sent and received are stored in RAM of the Arduino, or the ATmega 32AP. We'll say Arduino for short. The libraries that we'll be using kind of already handle a lot of the stuff with moving the buffered values to commands on the I2C bus. But if you're on a brand new chip, this would be something, as somebody's writing firmware, you may have to write these libraries to make it nice and easy. But the libraries that we're using have a fill, send, and read from that queue or from the buffer. A queue being that it's a first in, first out. So the first thing that arrives, you'll handle that one first, etc. And then it also has timing functions to let the system know when the data is ready. The actual specific library is called Wire. It's just kind of an Arduino specific library. And oftentimes on AVR-based Arduinos, you need specific I2C pins. If you're using ARM-based Arduinos, you may have some more flexibility. But the AVR ones, which is Arduino Unos and a lot of the ones we use on our teams, they have specific pins you have to use for I2C. So we have I2C device organization. So how is the device actually working? It contains a bank of kind of control and data registers, which can be read or written to. So we were, last week we were working on registers. So we'll be doing the same exact thing. As a reminder, registers are kind of specific locations of memory or information that are being stored. So you have an address, a register address to indicate the next location of reading. So you say, okay, I want to look here, and then you look through the table of registers. You get to the line you want that you requested, so that's that register address, and then it sends you the information, or if you're trying to write to it, it goes to that place and reassigns the values at that register with what you want. So the master can set the value of the current address and write or request data at that location, and that's kind of what determines what the device is the master. So consistently, we're going to have the one Arduino in the lab be the master, and then the second Arduino, which will actually be representing a IMU, which I'll get into the lab in a little bit, but that'll be our secondary or our slave. So reading and writing, if you remember the packet, there's the that reading and write bit. You'll be using that. The library is going to include that, kind of handle that. But you'll be reading send memory location to the device and send the stop condition in the wire library, and then the device will respond with the data stored in that request location. And then writing is, I guess, more straightforward. You're just saying, okay, please go to this place and write this value, or write this register, right? And then in both cases, the device actually automatically increments the register address, because it's very unlikely for you to constantly be wanting to write on the same place. It's more likely to be, I want to update a whole list of things, right? So what it does is it writes the first one, then it goes to the next register automatically and writes, right? So then you can pass, a bunch of characters across the I2C bus and write to those addresses more efficiently, rather than saying, okay, now go to this one, being more explicit with that. So here's some example code. Like I said, in the lab, we can get more specific into it, but you have to start the transmission with the specific address that you want. It's usually in hex, as we covered previous weeks. we'll write to the register that we want, and then you'll do, end transmission. These specific parameters, you can look up the wire library and see what they all mean. But they also have, we're going to request from the specific address and that number. And then while we're kind of waiting for it, or while there are still characters to be read, we'll continue to read them. So like I said, we'll get more into it in the lab. So this lab's a bit different. So of course, if we were in person, it would be great to be able to give you all some hardware. But of course, given the situation, we had to kind of simulate some hardware. We've been using Tinkercad for the past 2 weeks, and we wanted to do an I2C device. But fun fact, there aren't actually I2C devices in Tinkercad. So we made ourselves a simulated version. But the thing we made a simulation version of is the MPU 6050. So this is a really common type of IMU. I think it's no longer being supported, made, I don't know, but it's so many years of being used. It's been pretty common. Marine, do you have some? Yes, okay. Marine was just letting me know that RoboCup has used the IMU in the past. So it's pretty common in robotics now, just because it's been around for, it's like the Arduino Uno, right? It's just common because it's been around for so many years. So it contains a 3-axis accelerometer and 3-axis gyroscope. So that is how you can kind of convey, linear acceleration in, X, Y, and Z, and gyroscopic in yaw, pitch, and roll, I believe. So it's all the different plane terms for describing rotational acceleration. Or position, right? So the device itself, real device, communicates over I2C. So we will, in the lab, kind of initiate communication with the sensor. Then we'll read from the Who Am I register to kind of confirm the address. It's a really common thing to do with I2C. When you make a new PCB, or when electrical people hand the firmware people new PCB, don't always know the PCB is made right the first time. Could be assembly, could be whatever. So it's always great to read the Who Am I register to see, something. And usually those are consistent responses. So we will read from the Who Am I register to confirm it's correct, and then we'll write to the power management register. So the specific chip, it's used in phones and other things, or has been. And power management is important. So they have a specific register to actually turn it on. And then we'll read from the acceleration registers to measure kind of the force in the directions. We'll extrapolate it out, gravity. And then we'll kind of convert those accelerations into angle measurements. And the end goal is actually to make up a digital level. So it's like if you've seen, the old-fashioned bubble levels, where if you tilt it one way, the bubble goes down. If you tilt it the other way, the bubble goes the other way. We'll be making those with our LEDs and our IMU.